Hi there, this video is on section 4.4, part 3, which is going to be the second fundamental theorem of calculus. So in part 1 of this section, we talked about the first fundamental theorem of calculus, right? The FTC says that when we integrate from a to b, f of x with respect to x, that ends up being the antiderivative of lowercase f, which we represent as capital F, of b minus capital F of a. Okay, so that difference, that's our first fundamental theorem of calculus, at least in this textbook that's referred to as the first one. So our second fundamental theorem of calculus we're going to make sense of next. So if a function f is continuous on an open interval I containing a, then for every x in the interval, this statement is true. Okay, so let's kind of think about this from what we know, right? Like we know that if we were to think about rewriting this definite integral, just this part, using the first fundamental theorem of calculus, right, we would have that the integral from a to x of f of t dt would be equal to capital F of x, right, capital F of b, that would be capital F of x minus capital F of a. Okay, where capital F of x is the antiderivative of lowercase f. Okay, well, if we thought about taking the derivative of each side of this equation with respect to x, okay, well then now this side, the left-hand side, matches up with that statement in the second fundamental theorem of calculus. But then looking at the right-hand side closer, well, the derivative of capital F of x would be f prime, right? Well, since capital F of x is the antiderivative of lowercase f of x, wouldn't this actually just be equal to lowercase f of x? And then the derivative of capital F of a, or minus capital F of a, well, capital F of a would be a constant, and the derivative of a constant is just 0. So that's one way to make sense, or to kind of wrap your brain around what this statement is saying in the second fundamental theorem of calculus. But if you want to pause the video right now and work through this kind of geometric derivation representation of the second fundamental theorem of calculus, you could do that now. So you could pause and then go back through to check your answers. But I'm going to talk you through this. And this is something that Mr. Green created that I'm referencing. Okay, so if we let f of t equal to t squared, so that's graphing where our outputs are f of t, our inputs are t, so our horizontal axis is t, and a of x is the area between the graph of f and the t-axis. So a of x is shaded in there in yellow from 3 to x. So that means that a of x would end up being equal to, well, this is a positive function on a closed interval, so that means that the area can be represented by the definite integral. In this case, from 3 to x. And then our function is t squared, so it'll be t squared dt. So this will be our area function. So we are thinking of the definite integral as being a function of x. As x increases, more area will accumulate under the graph of f. So a of x is referred to as an accumulation function. Sorry, I'm having a hard time saying that right now. I think because I'm stuffy. And you're going to hear this term accumulation function come up again. So just kind of planting the seed for now. So you wanted to evaluate a of x for 5 different values of x. You could just evaluate the definite integral for each x value using the fundamental theorem of calculus. So plugging those different values in for x and then evaluating using that first fundamental theorem of calculus. But there's actually an easier way. You can treat x as a constant temporarily and apply the fundamental theorem of calculus. So if we think about just applying the fundamental theorem of calculus to our a of x function, okay, when we integrate t squared, thinking about using power rule for integration, that would be 1/3 t cubed, or you could write that as t cubed over 3. And then finishing applying fundamental theorem of calculus, that would end up being x cubed over 3, or 1/3 x cubed minus 3 cubed divided by 3, which would be 3 squared, or 9, minus 9. Okay, well that's a little bit easier. Now I can just actually plug in values for x, right? Like now I've rewritten a of x in this alternative form, which is not always possible, right? Because you don't know how to integrate every function out there. But in this case, we were able to apply that first fundamental theorem of calculus to rewrite a of x in a simpler way. So now we can determine like a of 3. If we plug in 3, well, that would end up being 3 cubed divided by 3 is 3 squared, or 9, minus 9 would just be 0. And then a to the 6 would be 6 cubed divided by 3 minus 9. And you could simplify that. Okay, so if you take a of x, which we said is that definite integral from 3 to x, or x cubed over 3 minus 9, and then we differentiate, notice what we get. We just get x squared, right? 1/3 x cubed, when we use power rule there, that just becomes x squared, and then the derivative of minus 9 is just 0. So a prime is x squared. So notice here, which from what I was saying before when I first showed you what the second fundamental theorem of calculus is, that the derivative of a of x is x squared. So where I was just able to think about replacing that t with x. Now, what do you think the derivative of the definite integral from 2 to x would be? So notice that the only thing that's changed here is the lower limit of integration. What do we think that would be equal to? Okay, think about it. If we reference this example, if this were a 2 instead, what would happen? Wouldn't this constant just be different? And the derivative, then whenever we go to find the derivative of constant will always be 0. So guess what? That derivative will just end up being x squared as well. So we can generalize, and that means that in general, whatever a is, we could just say that the derivative of this accumulation function would be x squared for some constant a. Now, what if f of t were t cubed? Well, think about it for a second. It's the derivative of the definite integral here, right, of this accumulation function. So it would end up being x cubed. Okay, so to summarize, the derivative of the definite integral from a to x is equal to lowercase f of x. Provided f is continuous on some open interval containing, we need it to contain a. So it has to be continuous on open interval containing a. Okay, so this second fundamental theorem of calculus is important because it guarantees that every continuous function has an antiderivative. Every continuous function has an antiderivative. Right? And we can always set up an integral, a definite integral, where that upper bound is x, that can represent the antiderivative function. Now, we can't always integrate, but we can still be able, and you'll see this coming up in the future, we can still set up a function knowing that as long as a function is continuous, it will have, it has an antiderivative. Sorry, I was saying that wrong. Okay, so now using the second fundamental theorem of calculus, let's find f prime, capital F prime. Well, if we're given that capital F of x is equal to the integral from 0 to x of sine of t dt, note that f of t, sine, is continuous, right? We know that sine function is continuous. That means that the derivative of this definite integral, capital F prime, would just be sine of x, applying the second fundamental theorem of calculus. And capital F of x being equal to the definite integral from -1 to x of this polynomial function, which is t to the 5th minus 9t cubed. Polynomials, you guys know, are continuous everywhere. So applying the second fundamental theorem of calculus, this would just be equal, the derivative would just be equal to x to the 5th minus 9x cubed. Next example, slightly different. This isn't just x. This is x squared. So at first glance, second fundamental theorem of calculus does not apply. Technically does not apply. We can kind of think, I'm going to show you how you can kind of think of a more like general second fundamental theorem of calculus being applied. But let's work through this using what we know. So because the upper limit is x squared rather than x, technically second fundamental theorem of calculus doesn't apply. So to get around this, we're going to do what we did earlier and express a of x as a function of x. Okay, so and what I mean by that is we're going to apply the first fundamental theorem of calculus here, right? When we integrate cosine of t, we should get sine of t. And then applying the first fundamental theorem of calculus, we get this difference. So sine of x squared, and that's of x squared, not sine squared, that's sine of x squared, minus sine of -2. Well, if that is capital F of x, right, this is just another way to write this definite integral. If we think about finding capital F prime of this, okay, Well, we know how to do that, just using rules of differentiation. Right? So capital F prime will be the derivative of that. So to differentiate sine of x squared, we have to think chain rule. Right? We have to think outside function, inside function. So derivative of the outside would be cosine. Leave the inside alone, times the derivative of the inside. And then minus the derivative of sine of -2 is 0. This is just a constant. So the derivative of a constant is 0. So this capital F prime ends up being cosine of x squared times 2x. If you want to rewrite that as 2x times cosine of x squared, you can. So more generally, my kind of more general second fundamental theorem of calculus would be if you're thinking about, here, I'll do this in a different color. So d over dx of a to, not x, but how about another function like g of x of f of t dt. Okay, this ends up being equal to f of g of x times g prime. And the reason we don't have to really think about this whenever that upper limit of integration is x is if you're plugging x in, well, and then you multiply by the derivative of x, like thinking chain rule, the derivative of x is just 1. So you don't really have to think about that. So if this upper limit of integration is anything else, well, can't see it there, anything other than x, you could kind of think about this more general form of the second fundamental theorem of calculus, or you can attempt to rewrite like this and then take the derivative. Either way works. Okay, so let's look at a couple examples here. So the graph of lowercase f of t is given. Let capital F of x represent the definite integral from 2 to x of f of t dt. So capital F of x is an accumulation function. So it's thinking about starting at 2, right? Letting x be different values. And when the function's positive, that's representing capital F of whatever the value is representing positive area. If depending on what x is, if there's negative area in there too, then you have to take into account net area. But let's go ahead and let's use what we've been doing in previous sections, right, to calculate area of a region. And let's go ahead and determine what these values are. So f of 2, that means this is going to be 2 to 2. Oh, this is a property of definite integrals. That'll just be 0, right? When the lower and the upper limit of integration are the same, that's just 0. F of 9, so 2 to 9. Oops. 2 to 9. So 2 to 9 to here. So we can think about finding the area of this trapezoid, which would be 1/2, or you can split that into a rectangle and a triangle and add those areas together. It'll be 1/2 times, looks like this side would be, what is that, 2 to 7, so it would be 5 plus 2 to 9, which is 7, and then it looks like the height is 20. Okay, so then to simplify that, what that would end up being 10 times 12, so 120. And f of 15, so that'll be 2 to 15. And again, you can pause the video if you would like and see if you can find the answers on your own, and then just check with mine. Okay, so 2 to 15. Where's 15? There we go. So we want this positive area plus this negative area. Well, we know what the positive area is. So it'll be minus whatever this area is below the x-axis. So we can use area of a trapezoid again. So 1/2 from here to here is 7 to 15. Or sorry, 9 to 15. Sorry, 9 to 15. So that'll be 6, right? Yep, 6 plus 4. This looks like 4. And then the height is 10. Okay, so simplifying that, that would be 120 minus 50. So is that 70? Okay. And then f of 18 would be 2 to 18. So we can actually take what we have here. I'm going to move this over here. So we can take the 70, and then we can add this positive area, which we can calculate using area of a trapezoid again. So that'll be 16 to 18 is 2 plus 15 to 18 is 3, and the height is 10. Oops, I erased this 0 there. Okay, so what is that? 5 times, that'll be 25 plus 70, so 95. Okay, and then f of 0. Oh, interesting. 2 to 0. Well, that's going in the reverse direction, right? That's going from 2 to 0. We've talked about this before when we were talking about properties of definite integrals. We could think of the delta x's as being negative in this case. So we can rewrite this definite integral and switch the lower and upper limits of integration, but we have to have this negative out front. So from 0 to 2 of f of t. Okay, so then from 0 to 2, that's a triangle with area 1/2, base is 2, and then height is 20. So negative 20 would be f of 0, capital F of 0. Okay, this next problem is kind of similar to this first part. So let g of x be the integral from 0 to x of f of t, where f is the function whose graph is shown below. So this is the graph of f. Okay, so g of 0, g of 2, g of 4, g of 6, g of 8. So we're going to estimate those values geometrically. So using our geometric formulas, right? We're given the graph of f. So area, positive, negative area between the curve and the x-axis. So g of 0, and again, if you want to pause and then check your answers, you can. G of 0 would be 0 to 0. That'll just be 0. G of 2 would be 0 to 2. 0 to 2, that's going to be a negative value because it's negative area. It looks like we can approximate that area using area of a triangle. So 1/2 base of 2, and then the height. And this is going to be negative, so I can either think of that as negative height, or I can just apply the negative and think about calculating the area of that triangle. The height is 4, so it'll be -4. And then g of 4, okay, so 0 to 4, still negative area. Our base is now 4, the height is still 4. So -8. And it looked like those triangles were the same. Okay, g of 6. G of 6. Okay, so we can take that negative, so 0 to 6. This will allow us to take that negative area, so -8, and then add the area of this trapezoid, which will be positive. Okay, so that's going to be 1/2, and then 2 plus 1 times the height is 4. So that's -8 plus 6, so -2. And then g of 8, okay, well that allows us to just take -2 and add the area of this trapezoid, which looks like it is the exact same, so +6. So it ends up being an area, the definite integral from 0 to 8, or g of 8, will be 4, +4. Okay, question B, find the largest open interval on which g is increasing. If we think back to like chapter 3, how do we determine where a function is increasing or decreasing? We look at the sign of its derivative. Well, in this case, g prime would be the derivative of the definite integral from 0 to x of f of t. Sorry, that should be a t. And we know by the second fundamental of theorem of calculus that this would be f of x, which would be the graph. We have the graph of f in front of us, right? So we can see that g prime is positive from 4 to 8, on the open interval from 4 to 8, and we can see that g prime is negative on the open interval from 0 to 4. So g is increasing from 4 to 8. So we can say g is increasing on the interval, 4 to 8, because g prime, which is equal to f of x, is greater than 0 on this interval. Question is not asking for justification, but I'm just giving it. G is decreasing on the interval from 0 to 4 because g prime, which is f of x, is less than 0 on this interval. Okay, and then identifying any extrema, well, g changes from decreasing to increasing at 4. So that means that there would be a minimum at x equals to 4. So g has a minimum at x equals to 4. You could say because g prime, right, which is f of x, changes from negative to positive at x equals to 4. Okay. Yeah. Okie dokie. Let me know if you have any questions.